Is that good?
Mm-hmm.
Awesome. So I'm a faculty at Lamar University. We are basically located at Beaumont. We are 90 miles away from Houston, east of Houston. So I graduated from University of Arizona in 2016 from Systems and Industrial Engineering Department, and I got a job in Lamar University. My research as a doctoral student was mostly about game theory, very theoretical NSF-funded projects. It was like about just theorems, proof, proposals. And then I got this job, and it was a very applied job focused on the waterway operation. And I had no idea about waterway operation. So when I got the job, I started attending different waterway, mostly at the Port of Houston meetings, that what are they doing? What are the questions? What do they want to solve? What are the challenges? So this Port Center also that we had a master's degree. So in addition to the doctoral program that we had in industrial engineering, we had a master's degree in port management that I really needed to know about the waterway operations so that I could develop the course for this master's degree as well. So during the very first meeting that I attended at the Houston Ship Channel or Port of Houston waterway operation meetings, there was a question that was a room full of attendees, and they were talking that they wanted to do a closure for the waterway. And the question was that, do we do the closures during the nighttime or do we do it during the daytime? There was no modeling, no results, no analysis, nothing. Just the people based on experience and intuition, they were talking about if they should do it during the daytime or the closures during the nighttime. So let me tell you the story about this Houston Ship Channel. Houston Ship Channel basically is a 50-mile waterway. So it starts from the Gulf of Mexico and the Galveston Seaway and goes 15 miles all the way to the downtown Houston. This Houston Ship Channel is #1 petrochemical complex in the USA. So basically, if this waterway is closed for some days during the hurricanes, the price of the gas actually goes up in Dallas and throughout the Texas because all the refineries that are alongside this waterway, they basically supply all the gas through the Texas and even abroad, nationally. So this is a very important waterway that needs to operate basically 24/7. What happens is that these big vessels that come from China, Asia, or basically South America, basically the captain of the vessel is in charge of controlling the vessel until they come to the Port of Houston or the USA waterway. Then after that, what happens is that a pilot is assigned to this vessel to control the vessel along this 50-mile narrow waterway. So basically, this pilot knows everything about this waterway. What it means is that basically the bottom of this Houston Ship Channel and many of the waterways, like the Sabine-Neches waterway, they have mud at the bottom of the waterway. And these huge vessels, they are deep. So the pilot needs to make sure that the body of the vessel or the bottom of the vessel basically does not touch anywhere along the side or along the bottom. So they basically need to dredge or dig this waterway constantly to make sure that the depth of the water is good enough for the vessels. So this is one of the responsibilities of the pilot. So what happens is that different vessels come to the seabuoy, they stay there, they anchor there, and they ask for a pilot, and then the pilot comes and takes this vessel and control it along the water. Another thing about the Houston Ship Channel is that there are 150 different refineries and different terminals along this waterway. So it's a very busy and congested waterway. They have cruise, as you know, they have Galveston cruise terminal, they have container terminals, they have different cars that they get imported to USA, and mostly oil and gas and refineries that are along this waterway. One of the issues is that this 50-mile waterway, because it goes through Houston, there are 5 bridges across the waterway. So what happens is that the vessels need to pass below these 5 bridges to get to their destination. Can you guess what can be the issue if the vessels need to pass below a bridge? What issue can it have? Any ideas? You can use microphone, you can use chat box. I don't know how to communicate with you, but my question is that, do you know what can be a challenge to have a vessel pass below a bridge?
Probably the height would be, not better. Or it can get it stuck in the queue to.
Correct. I don't know who is talking to me, but yes, that's correct. It is the correct direction. So one of the things definitely, as you are mentioning, is the queue of the vessels at the seabuoy and also the queue that they have at the terminal when they want to use the waterway to come back. Correct. And another thing is that they call it air draft. So definitely same as the depth of the waterway, that the vessel should not touch the bottom of the waterway. The vessel should not also touch anything above the vessel. So they call it air draft. So they need to make sure that the vessel do not touch the bridge, definitely. I mean, they have antennas, they have lots of things above the surface of the bridge that they need to make sure that the air draft is good. Some of the times when the vessel is light, the vessel become more above the waterway, so they have an issue that it might touch the bridge. So they call it bunkering, meaning that they put water in the vessel to make it heavy so that they don't have an issue with the air draft of the vessel and it doesn't go to touch the bridge. So what they do is that they bunker it and they make it heavier to make sure that the vessel is not touching anything on the bridge. So one of the things was that one of these bridges was going to be replaced. So if I show you the bridge, they call it one of the busiest bridges at the Houston. It's Beltway 8 bridge. So this is one of the pictures of the Beltway 8 bridge, a very congested bridge. So right now the bridge has two lines, and they call it north side, and two lines south side. So basically northbound and southbound, it's 2 lane each side. The plan was that they wanted to build a new bridge that is 4 lanes southbound. Then they wanted to demolish this old bridge and transfer the traffic to the newly built bridge, and then build another bridge for the northbound, which is another 4th lane. So 4 lane, 4 lane, and then demolish that one in between the construction of the 2 bridges. Now the whole question was that for this construction, each of the constructions, so construction of the southbound was exposing 55 number of closures on the waterway. Then demolishing this old bridge was another 33 number of the closures, and then construction, the new 4 lane northbound was another 55 closures. So it was a great number of the closures for the waterway. But the good thing for the waterway was that they were going to increase the air draft. So these new bridges were supposed to be taller than the older bridges. And another issue was that the tower of the current bridge is in the waterway. So basically they couldn't service a wide bridge, a wide vessel, because it could basically touch the tower of the bridge. So they could, I mean, with the new bridge, they can make the waterway wider because they don't have this tower in the water. And also the height is going to be more, so they could have a higher air draft. So it was good for the waterway. So they accepted that, okay, we were going to have this number of the closures on the waterway, but it will have advantage for the future traffic. Now the waterway, they were discussing this important issue, and then there were no modeling. Basically, they were just talking. Okay, somebody said, let's do it during the nighttime. Another person said that let's do it during the daytime. I predict that the congestion would be less if we do it during the daytime. So how I looked at the problem was that, okay, it's like a bank that basically the customers arrive at the bank, they get a service, and then they go back. So do you have any ideas what can be a good modeling for these type of questions, that basically some customer arrive at the system, they get some service, and then they go back out of the system? Do you know what can be a good methodology to model this type of questions? Any ideas? So do you know what methodology did I use? Can you guess? Do you have any suggestion?
Okay, this is, fairness again. So I don't know, maybe queuing theory or dynamic programming. That
Thanks, yes, exactly. So basically, when I first time saw it, I saw that it's very much close to the like the non-homogeneous Poisson process and queuing theory. That basically these vessels are like the customers that they arrive at the system with some arrival rate, and then they have a service time. There are some resources that basically the resources was these different terminals that they were going to seize for a specific amount of time, and then they release the resource, and the next customer can basically go and seize the resource and use it, and then they leave the system. So that was exactly the same thing that came to my mind, that we can model it based on the non-homogeneous Poisson process, and I basically used Arena to model the waterway. So that is exactly correct. The waiting time, and I was looking at the waiting time, that if we do the closures during the daytime or the nighttime, which of them is going to have a better waiting time for the whole system. There are many closures at the waterway. They can be as a result of the fog. So when the visibility at the waterway is not enough, they cannot basically navigate the vessels because there is a risk of collision. So when there is fog, there are some partial closures. When there is constructions, as I say, for the bridge construction, they are going to close the waterway. When they have expansion, so when they want to widen the waterway, for example, again, they are going to have all types of these closures. Another very important thing is the dredging, that they basically need to dig the waterway for the muds. They constantly need to do that. So there were all reasons for the closures, that they needed to have a good schedule or optimal closure time for these closures. Basically, the impact of this closure was really huge, that it was comparable to the oil spill. The Army Corps did a research and say that this closure had really impact on the waiting time of the vessels. And another issue about the waiting time of the vessels is that these vessels basically, they wait at the Galveston Seabuoy, and all the time they are basically consuming fuel. So it's not good for the environment. This congestion has risk because they can collide during these congested hours. And then the cost of transportation, that the more they wait at these seabuoys and anchorage areas, basically the consumers are going to pay for these products at the end. So as you see that in LA Long Beach, as you see what's happening for the containers in the California, so definitely when Target or Walmart are going to sell these products, the consumer has to pay for this waiting time there at these seabuoys. So it has economical impact. So what we were going to do was that, what is the best time to do this closure? Do they want to do it during the nighttime, or do they want to do it during the daytime? So basically what we did was that we had different scenarios, right? If they started at 7 p.m., so it was a nighttime closure, what time at the night they want to start, and then what is the pattern of the closure? They could close for 9 hours straight, or they could have an opening window in between, that, for example, for 2 hours it is open so that basically the vessels could pass, and then they close for another 5-6 hours after the opening. So there were different scenarios that they were asking me that, look at these different scenarios and tell us which of these would be best for our modeling. We had different data. So the Houston pilot provided us all the data for the arrival of the vessels for 2 years. So basically we could have an arrival rate that during each hour, on average, how many vessels arrive at the system. So basically we had an arrival rate for a non-homogeneous Poisson process, that the vessels arrive based on this distribution to the seabuoy. And then when this vessel arrive at this seabuoy, what is the demand for each of these 30, 40, 150, basically number of the terminals? How is the demand distribution for each of these resources? And then there was a travel time from the seabuoy to the destination, that we fit a distribution to see that what is the best travel time or random distribution for the travel time of the vessels from the seabuoy to the destination that they have. And then we needed to know that what is the process time, so how long each vessel is going to seize the resources, which are the docks and the terminals, what is the process time that are going to get the resources basically busy. So we put a distribution for the process time. As you can guess, for the number of the resources that existed, some of the terminals had more than one dock. So we had to put that in the arena simulation that how many docks is available or how many resources do we have for the system. So when we considered all these scenarios, we came to the conclusion for the basically for the decision makers that basically the results show that this was a flowchart of the model. Let me show you that one. This was a flowchart of the model that basically the vessels arrive at the seabuoy if the destination dock is available or not. If it is not available, they need to wait at the seabuoy. If it is available, then they get a pilot and basically leave for the terminal. They will basically seize the resources for a specific resource for a specific process time, and then they will again get a pilot and then leave a system. So this was a flowchart for the modeling. And then, as I said, we looked at different closure scenarios. We got the final result that basically the results show us that it was a 24/7 hallway, and basically there's no recommendations for daytime or nighttime closure. There were no difference basically because the vessels, they were there 24/7. They had to give service. So basically daytime or nighttime closure didn't matter that much. But what mattered the most was the pattern of the closure, that they needed to have an opening gap in between closures. So if they close for 3 hours, they needed to make sure that they have a 2 or 3 hour of opening, and then they close again for 2 or 3 hours after that. So some of the results of the modeling was big. I mean, we couldn't share all the results with you, but the basics of the modeling I could share with you. So this is how we actually addressed and told them that this is the optimal closure of the waterway, which is a really important waterway. So as you see, I mean, during the PhD, you work with some tools and then you get a job that has nothing to do with what you have done. I mean, it looks like it has nothing to do, but it actually, when you know these tools, you can apply them on many different research questions and it can really be effective. So yeah, do not be risky and just go through your passion, what you like to do, and make sure that you learn a lot of the tools throughout your degree so that you can use it in the future. So Sepide is my doctoral student. She has done many research along the waterway and the AIS data. So basically what happens is that the vessels, same as the cars that they have GPS, the vessels have AIS. So basically this device that they have, every 2 seconds or 5 seconds, they transmit the location of the vessel, the draft of the vessel, the direction, the speed, so many different information about the vessel. They transmit it throughout different antennas that are along the waterway. So they can be done, it's a huge data set, as you can imagine. And then you can do a lot of cool research on the AIS data that Sepida will continue and give you some idea how you can use this AIS data to get some cool results for decision-making processes. So if you have any questions for me, please go ahead and ask. If you have any question, please go ahead and ask me. Sepida, meanwhile, please go ahead and share your screen.
Mariam, I can ask a couple of questions. So is the building the new bridge, is it an ongoing process or it's already finished?
Yes, good question, Sarah. I mean, these basically constructions is really time consuming. So basically, I think originally it was a 5-year project to replace this bridge. Right now, they have not started closing the waterway, but they are working at the side band of the bridge. So they have to build it from basically from the land. So they are building that part, and there is a live video that every day we go and check the progress of the building. So they are still building the first bridge. They have not demolished the old bridge, but they have not reached to the waterway closure. So they're still working on the land side.
And then my follow-up question, I asked that question to see, so you fitted your arena model based on the historical data, right?
Correct.
nowadays that, COVID has impacted everything, how you can make sure that the model is, holding up with the new disruptions that are happening everywhere?
That is a good question, Sarah. We didn't basically use the most current data to update that one, but I think COVID affected all the daytime and the nighttime vessels the same way. I don't think that it really COVID, yes, they had a decrease in the vessels that they get service at the waterway, but I think that it was uniform throughout the daytime and the nighttime vessels that passed. So I don't think the result would change that much if they closed during the daytime or nighttime. But I think by the time that they reach the waterway, the congestion would be the same as pre-COVID time and even more congested, as you see in LA Long Beach. That's a good idea that we rerun the model for the exact time that they actually start doing the closures of the waterway. That's a very good idea, sir.
Okay. Any other questions for Dr. Hamidi? Okay, then maybe we can go ahead and listen to the next part of the talk.
We'll go mute and Sepida, you can start.
Hello, everyone. You can hear me?
Yes.
Hello, everyone. This is Sepide. I was Dr. Hamidi's student. I graduated from Lamar University at July. And I've been working on the Houston Ship Channel and the traffic conditions using AIS data for the last 3 years. Here's the topic of my dissertation, that quantifying waterway traffic conditions using AIS data and optimizing vessel schedule. And our case study was Houston Ship Channel. Here's the outline of the presentation. I just talk a little bit about the introduction and the 3 different chapters I worked in this thesis: traffic conditions analysis, traffic delay quantification, and vessel scheduling optimization. I can put it in. Okay. First of all, I should say that why we choose this topic for or project and or dissertation. The necessity of why this topic is important. One of the reasons is that these days the traffic demand for the waterway is increasing since this mode of transportation is very cheaper than the others, and so for most of the commercial commodities, this technique, this method of the mode of transportation works best. So we are witness of increasing the waterway traffic demand, and this makes the problem in the traffic conditions and makes traffic congestion near the port areas. Since in the ship channels near the port areas, there are different navigation restrictions, as Dr. Hamidi said, such as daylight restrictions, that some chemical tankers could not go through the channels during the night times, and or width restriction, that some vessels could not pass each other in some restrictions, or channel closures because of the bad weather or dredging or some different some accidents. These problems make the congestion and traffic delays even more important to consider. And every day the vessel size increases, so this makes the even more important to focus on this topic. Besides of all these problems, because these vessels have to wait a long time in anchorage area, they had very harmful emissions that make environmental issues in those areas. So because of all these problems and issues, we decided to work on this topic and decided to use the AIS data to find out the traffic conditions in different parts of the channels and develop a methodology to quantify congestions and different traffic measures from the AIS data to help the managers in port areas to focus on their problems and their issues. So I've done extensive literature review in this process. I try to work on different modes such as roadways, airways, and waterways to know how they work on this topic, what kind of data they use, which kinds of methods or analysis technique they use to work with this kind of data and extract the useful information from that, because as you know, the trajectory data is not very useful by itself because it's just points of the vessels in different parts of the ocean or the ship channels. But to make it work and make it useful for the research, we should use, for example, trip separation and kinds of analysis to prepare this data for further analysis and extract information from that. So here's the research problems that I worked on it. First of all, I try to use the AIS data to analyze the traffic conditions in waterways and cope with the long waiting times and challenges in the waterways and channels, specific the narrow ones. And quantifying the system's traffic delay because of the width restrictions in waterways, and finally develop a scheduling optimization model to improve the waterway utilization and decrease the vessels' delay during their journey. As Dr. Hamidi told you about how this waterway works, you can see in the figure that there is two deep draft lanes at the middle of the channels and two or more low draft lanes at the end of each side, that deep draft vessels could use the middle ones, but barges or tugs, these kinds of the low draft vessels could use these low draft lanes at the sides of the road. Size of the channel. Since there are different restrictions in the channel, the pilots of these vessels, these deep draft vessels, could not navigate in these waterways, and there are professional pilots that are assigned to these vessels, and so the marine pilot organizations are established to manage vessels navigation. According to different waterway restrictions, they find the best possible time for each of these movements, and so assign the professional pilots to the vessels, and then they could go through the channel. In this way, they could avoid collisions or grounding in the channel. In this project, I use AIS data, which was developed to monitor the ship traffic with position and speed measurements for uniquely identified ships, and also it shows the movement of all vessels type in the coastal seas and the offshore areas. And besides of that one, I use the marine pilot data. It's a historical transit data, which provide us the details about the vessel movements in the channel, such as the original time that the vessel pilot is ordered. Because in the AIS data, we just have the information when the vessels start the sailing or stop the sailing, but we don't know where, when, and the time they really want to start their navigation. They put their request, but based on different restrictions, the marine pilot organization don't doesn't allow them to start navigation, and they scheduled a new time for them. But for in the transit data, we have that original time they requested for pilot time, and this could help us to find out how much they face with the delay, how much time they face with the delay, and it is so useful for us. The first part of this project, I worked on analyzing the traffic conditions in waterways and ship channels. First of all, we find and develop some traffic measures according to roadways and also the waterways previous works on this area. We found that some very useful traffic measures such as origin destination metrics, which shows the number of trips from an origin to a destination, trip generations, trip attraction, that the numbers of trips started or ended from or in each node, average travel speed, traffic flow, traffic density, and here's the traffic measures we used in this project. And then we develop a methodology and we develop an algorithm to extract this information and these traffic measures from the data. So first we clean the data and we did the pre-processing, such as sampling, removing the noises and handling the missing points. And then we define as to make it more to handle, and we could visualize the data better. We decided to divide the channel into different segments. So we defined the segments polygon and assign all of the AIS points to their related segments. And then we separate the trips for each of those vessels. For example, first vessel started its navigation from segment 1 and it stopped at segment 4. So we consider that as a trip because, as I told you, just working with the points doesn't work and could not help us to extract the information. So we decided to separate the trips and tours. So we sort the data based on the unique code of the vessels and the date, and then we determine the direction, and then we separate the data to tour and trips. And then we have a final kind of data set to extract the OD metrics and traffic flow and average traffic speed, or all of the measures we want. So here's the math behind that quantification, and here's the picture of the whole process and whole algorithm to analyze, to prepare the data for extracting the traffic measures. I don't go through the details. So here's the finally, at the final steps, we applied our methodology on our case study for the Houston Ship Channel. As you can see, we divided our ship channel to 48 segments. Here is the seabuoy area or anchorage area, and here's the way the vessels go through. And from this area, the most of the docks and the terminals are placed here in this part of the channel. And we worked on AIS data for August 2018. And here is some information we extracted from the AIS data. As you can see, these parts of the channel and especially this area faced with high density, because most of the high demand terminals are placed over there, and as the vessels go through the channel, these parts of the channel is narrower than the other parts, and that they have to reduce their speed in this area. So we face with high density here, and here's the trip generation for low draft tankers. These areas are anchorage areas, and this area also, and these are the most popular terminals for low draft tankers. Here is the trip attraction as well, that these figures could help us to for expansion projects, for task scheduling, for practical for resource allocation of tasks. So here is the inbound or outbound OD matrix. As you can see that the deep draft vessels don't have a stop in the middle of the channel, but low draft has some stops in the middle. Here's the what we got from this project, that we could use the AIS data to analyze the either short-term operation plans or long-term. We could analyze the traffic conditions for blue waters or brown water separately, which means the deep draft or low draft vessels, and analyze the traffic conditions in a big pictures, as you can see, for the whole channel, and simultaneously for specific segments in details if we want. And then help the channel decision makers to find out their limitation, their weaknesses, the most probable congestion points or accident areas, and investing in the best expansion plan, which maximize the channel utilization and minimizing the project cost. So in the next chapter, according to this information, we try to find out due to width restriction, how long these vessels have to wait and face with waiting times. So to capture that waiting time and delays due to width restriction, we develop another algorithm. As you can see in this figure, if these two vessels could want to pass each other in this restricted area, one of them has to stop at its stationary point until the other vessels pass this restricted area, and then the other one could use that part. For example, in this figure, this vessel, this arrival vessel has the priority. So this gets the channel and go through the channel. And when it arrives to its destination, this sailing vessel at this dock could start its navigation. And because of this movement, it creates a delay or it creates a interval. In that interval, these vessels could not use the channel and could not start navigation due to that time interval. So in this process, in this chapter, we try to develop that time interval and then quantify the parameters and the variables in that time intervals, and that's how we could quantify that. For example, these vessels have to stop time between 1 p.m. to 3 p.m. because of these vessel movements, and this vessel requested for pilot at I don't know, for example, 12. So these vessels have to wait for it starts navigation for it's requested for pilot at 1:30. So it has to start until 3 p.m. So it faced with delay for 1.5 hours. So according to this process, we could quantify the traffic delay for whole months. Here's the how we define the share restricted. section based on the arrival vessel's destination or the stationary point for the these sailing vessels. And here is the how we quantify the conflict intervals. And then we capture the total delay for each vessels and then for each dock. For this methodology, we have to extract some useful parameters from AIS data. So we develop another methodology to quantify some parts of the information we want for this methodology. And then use the AIS, the pilot data to quantify the traffic delay. And then we apply the methodology on the Houston ship channel. And in this channel, you can see that we have 3 different width restrictions. And we apply the methodology and we find that, for example, for restriction 2, we have 11 impacted vessels for about 10 hours in different docks. Or for third restriction, we have these about 311 hours for 107 impacted vessels on different parts of the channel on different docks. So we find that this methodology could show that how we could quantify the traffic delay from the information, and we shows that the AIS has some limitations, that we could handle that with the private data from the, for example, marine pilot organizations. We could empower it with those data, and we could help we can run this method for different prioritizing situation. For example, arrival vessels have priority, or sailing vessels or shift vessels, to find the best model and then use it for expansion projects. For the last part, I try to develop a model to optimize the scheduling scheme for vessel movements in Houston Ship Channel. I worked on 3 different restrictions: width restriction, daylight restriction, and channel closure. And here's some of the assumptions we have. For example, we consider we could assume that the dock is available for vessels. We just consider that we don't have the access to the channel all the time, but we have the ability to use the anchorage area or dock at any time we want. And we consider the bad weather as a closure time. We don't consider the pilot shortage. We consider 2 types of vessels here, tanker and cargo. And then we try to model the problem. We want to minimize the traffic delay, which is the time difference between the final scheduled time and the first pilot or original pilot order time for each vessel. And we consider different restriction, as I told you, that we consider that conflict interval, that the vessels could not use the channel, and we develop different restrictions and constraints here, and daylight restriction and channel closure are other constraints we consider in this model. And then I try to use the exact method and genetic algorithm to solve this problem. Here's my genetic algorithm I developed. I I can say it here. I use, for example, each possible scheduling scheme. For example, vessel 1 gets the priority first, and the third one, and the ninth one, and like this. These could be a chromosome, an initial population, and then we use the fitness function and use the this method to crossover and mutation techniques in this genetic algorithms to optimize the model. And here's the termination criteria that we consider 50 generation as a criterion, and the ratio of difference between the highest and lowest value over the lowest fitness with value in each generation. And after that, we should use something to benchmark. For that, we run the model for a small size in an exact and use the exact methodology to solve the problem and use that for the benchmarking. But we could develop another method such as essay to compare the results together. And here's the example in this part of the project that you can see that the performance of the genetic algorithm with the exact method, that the time is very different from this one when the number of the vessels increases. And here's the final schedule scheme for 10 vessels based on the GA and the exact method. So here's the last part of my project that I worked on. And here's I have four different papers on different parts of the project. That one of them is online now, but the other ones under review. Thank you so much for your attention and having me in this seminar class. Thank you, Dr. Masood and Dr. Hamidi.
Wow, thank you, Dr.